Ayubawan, a very warm welcome to all you dear students to another lesson right here at Study Hub Sri Lanka. I'm so glad you could join me. I hope you're all ready and have a curious mind today.
Today, we're diving into a really fascinating part of chemistry, electron configurations. Now, I know, that sounds a bit complicated, right? But trust me, our goal today is actually pretty simple. We're just trying to figure out where do all the electrons actually live inside an atom. By the end of this lesson, you'll be able to map it all out, no problem. So, here's our game plan for today. First, we'll check into something I call the Electron Hotel. It's a neat little analogy. Then we'll learn the 3 golden rules that the electrons have to follow. After that, we'll get some practice writing down their proper addresses. And finally, the best part, we'll uncover the secret of how this all explains the shape of our beloved periodic table.
All right, let's get right into our first section. To make this whole topic a bit easier to picture in our heads, we're going to use a simple story, an analogy that I think will really help it all click.
Let's just think about this for a moment. We know that atoms have that nucleus in the center with protons and neutrons, and then the electrons are buzzing around it somewhere. But where exactly? How are they all arranged? Are they just flying all over the place? This is the core question we're going to answer today.
So, let's imagine the atom is a big special hotel. We'll call it the Electron Hotel, and this hotel is exclusively for electrons. Now the main energy levels, or shells, they're like the floors of the hotel. First floor, second floor, and so on. The subshells, S, P, D, and F, are like the different types of rooms on each floor. You know, maybe S are the standard rooms, P are the deluxe rooms. And the orbitals, well, those are the actual, individual rooms where the electrons get to stay.
Now, just like any good hotel, our Electron Hotel has some very important rules about how the guests, our electrons, can check in and take up the rooms. And honestly, if you understand these 3 simple rules, you've understood the whole thing.
Okay, rule number 1 is the Aufbau principle. It's a German word, Aufbau, and it just means building up. This rule is super simple. It just says that electrons are, well, they're a bit lazy. They will always fill the rooms on the lowest floors first, the ones with the lowest energy, before they even think about moving up to higher floors.
Now, have a look at this diagram. You can think of this as our map of the hotel. It shows us the exact order that the rooms get filled. You just have to follow the arrows. We always start at the top with 1s, then the arrow takes us to 2s, then 2p, then 3s, then 3p, and so on. This map makes sure we always place the next electron in the correct, lowest energy room available.
Rule number 2 is the Pauli exclusion principle. This is the hotel's room capacity rule. It's very strict. A maximum of 2 electrons are allowed in any single room, or orbital. That's it. And for 2 electrons to share a room, they must have opposite spins. Think of it like 2 little spinning tops in a box. One has to spin clockwise, and the other one has to spin counterclockwise.
Let's look at a real example here with lithium. Lithium has 3 electrons. You can see the 1s orbital, the first room. The first 2 electrons go in there. We draw them as little arrows, one pointing up, one pointing down. That shows their opposite spins. Now that room is full. So where does the 3rd electron go? Well, it has to go up to the next available room on the next floor, the 2s orbital.
And our last rule for today is Hund's rule. This is what I like to call the personal space rule. Imagine you have a set of rooms that are all the same on the same floor, like the 3p orbitals. Hund's rule says that electrons prefer to have their own private room first. They will only start pairing up and sharing a room after all the empty rooms of that type already have 1 electron each.
And carbon is the perfect example of this rule. Carbon has 6 electrons, so the first 4 fill up the 1s and 2s orbitals. But what about the last 2? They go into the 2p subshell. But notice, they don't pair up in the same little box. According to Hund's rule, they each take their own empty 2p orbitals first. They're not sharing it.
Excellent. Now that we know the 3 golden rules of our Electron Hotel, we can finally start writing the full address for every electron in an atom. And this is what we call the electron configuration.
And really, it's just a simple 4-step process. First, find out how many electrons you're working with. That's just the atomic number from the periodic table. Second, start filling the rooms using our Aufbau map. Third, remember Pauli's rule, no more than 2 per room. And fourth, follow Hund's rule for rooms of equal energy.
Give each one a single electron before you start doubling up. See? Simple, no?
Let's look at this table together and see how this builds up in practice. For lithium, with its 3 electrons, 1s gets 2 and 2s gets 1. So we write it as 1s squared, 2s1. For carbon, with 6 electrons, it's 1s squared, 2s squared, 2p squared. You can see the pattern clearly as we add more and more electrons, just following our rules every single time.
Now, writing out that long string of numbers can get a bit tiring, especially for bigger atoms. So chemists came up with a really clever shortcut. We can use the previous noble gas to stand in for all the filled inner shells. So for sodium here, the part that is 1s squared, 2s squared, 2p6, well, that's just the configuration for neon. So we just write Ne in brackets and then add the rest, 3s1. Much faster, isn't it?
This shortcut brings us to 2 very important terms. The electrons that are kind of hidden inside that noble gas symbol, we call those core electrons. But the electrons in the outermost shell, like that 3s1 electron in sodium, we call those valence electrons. And these are the superstars. You must remember, the valence electrons are the ones that do all the work in chemical reactions and bonding.
Okay, so we've got the rules, we know how to write the addresses. Now for the really amazing part. Let's see how these simple rules are actually the secret blueprint for the entire periodic table.
I mean, really, have you ever just looked at it and thought, why is it shaped like that? Why are there these blocks and these gaps? It's not random at all, you know? There is a beautiful, logical reason for it, and it all comes back to our electron hotel.
And here's the big secret. The periodic table is literally a map of the electron orbitals. Those first 2 columns on the left, that's the s block, where the s orbitals are being filled. That big block on the right is the p block. The transition metals in the middle, that's the d block. The whole shape is a direct result of the order that we fill the orbitals we learned with the Aufbau principle. Amazing, isn't it? It all fits together perfectly.
And because the table is organized this way, elements in the same column or group have the same number of valence electrons. This is why all the alkali metals in group 1 behave so similarly, and why all the halogens in group 17 are like a family. Their chemical properties are directly linked to their shared electron configurations.
So, the most crucial point to take away from our lesson today is this. These 3 simple rules, Aufbau, Pauli, and Hund, they aren't just some abstract ideas. They are the fundamental principles that dictate how electrons arrange themselves. And in doing so, they create the entire structure and logic of the periodic table, which is the foundation of all of chemistry. I really hope this explanation made electron configurations much clearer for all of you. If you found this lesson useful, please do consider subscribing to our channel, Study Hub Sri Lanka, and don't forget to click that little bell icon. That way you'll get notified about all our next lessons and study tips videos.
Thank you so much for joining me for this lesson, children. It was a pleasure teaching you all. Keep studying hard, always stay curious, and we will meet again very, very soon with another lesson from your science subjects. Have a wonderful day.